So here we have our full adder project, lab 2, using two half adders. And so to start off, we declare the inputs A, B, and C, and our outputs final sum and final carry. We also declare sum 0 and sum 0, 1, as well as carry 0 and carry 1 for our inputs for the individual half adders. And now we call in the half adder module by making two instantiations, one of them correlating input A to input A, B to B, sum to sum 0, and carry to carry 0. And we have half adder 1, which correlates input A to sum 0, input B to C, sum to sum 0, 1, and carry to 1. And now we declare final carry, which is equal to carry 0 or carry 1, and final sum equal to A, X or B, X or C. And we can see our schematic here. Now we'll run through the test bench code, which was provided through the lab manual. And what this essentially does is calls another instantiation to correlate the inputs A, B, and C to T, A, T, B, T, C, and same with F sum and F carry to T out sum and T out carry. And this essentially just gives our inputs from 0, 0, 0 to 0, 0, 0, 1 for every single test case with a spacing of 5 nanoseconds. And we will see the output in our timing simulation, or behavior simulation, right here. Let me run that again. So here's the behavioral simulation using the test bench code, and for all our inputs being 0, we get 0 on both our outputs. When c is equal to 1, we get sum 1. B1, when b is equal to 1, we get sum 1 as well. When b and c is equal to 1, we get 1 on the carry, 0 on the sum. Whenever a is equal to 1, we have 1 on the sum. Whenever a and c are equal to 1, we get 0 on the sum and 1 on carry. Whenever a and b are equal to 1, 1 on carry, 0 on sum. And whenever all of our inputs A, B, and C are equal to 1, we get both 1. We get 1 and 1 on sum and carry. And that concludes the behavioral simulation. Next, I will show the constraint file, and we will be using LED 0 and 1 for sum and carry, and switches 0, 1, and 2 for A, B, and C. Now I will move on to the physical demonstration on the FPGA. So here we have the demonstration of our full adder using two half adders. So for LED 0, that would be our sum. LED 1 would be our carry. Switch 1 is input A, switch 2 input B, switch 0 input A, switch 1 input B, switch 2 input C. And so when we enable input A, we have 1 on our sum, 0 carry. Input A and B, we have 0 on our sum, 1 on our carry. And input B, just 1 on our sum, 0 on our carry. A and C, we have 0 on our sum, 1 on our carry. C and B, we have 0 on our sum, 1 on our carry. And with all of our inputs enabled, we have 1 on our sum and 1 on our carry. And that concludes the demonstration of the full adder circuit on the FPGA.